Welcome to Lesson 15 of Applied Physics. In this lesson you will cover the following objectives. Understand the concepts of solid deformation, i.e. elastic modulus, and understand the concepts of density, buoyancy, and fluid dynamics. All objects are deformable. It is possible to change the shape or size of an object through the application of external forces. When the forces are removed, the object tends to its original shape. This is a deformation that exhibits elastic behavior. Elastic properties are usually best described by understanding ratios of various properties. In this case, the two significant properties are stress and strain. Stress is related to the force causing the deformation. Strain is the measure of the degree of deformation. The elastic modulus is the constant of proportionality between stress and strain. For sufficiently small stresses, the stress is directly proportional to the strain. The constant of proportionality depends on the material being deformed and the nature of the deformation. Note, the graphic shows the linear relationship between stress and strain. The slope of the line before it begins to break down is known as the modulus. Any activity, stress or strain, before reaching the breakdown point is generally repeatable. Once you reach the breakdown point, you have gone beyond the elastic limit of the material. The elastic modulus can be thought of as the stiffness of the material. A material with a large elastic modulus is very stiff and difficult to deform. Three types of stress include tensional, where you pull parallel to the direction you are trying to stretch something; compressional, where you are attempting to squeeze down a material to a smaller size; and shear, where the force is perpendicular to the direction that you are trying to stretch. Tensile stress is the ratio of the external force to the cross-sectional area. Tensile is because the bar is under tension. The elastic modulus is called Young's modulus. SI units of stress are pascals. The tensile strain is the ratio of the change in length to the original length. Strain is dimensionless. This image shows a piece of plastic which was placed under stress and photographed using polarized light. The various ringed patterns show the stress at random locations on the plastic part. Young's modulus applies to a stress of either tension or compression. It is possible to exceed the elastic limit of the material. It is no longer directly proportional and ordinarily does not return to its original length. If stress continues, the object may break. An example of a structural stress would be a cable holding up a meteorological tower used in the wind industry. Cables under tension oftentimes stretch and eventually break. Additional examples include the compression of cement pillars, which might be holding up turbine towers, bridges, etc. The compressibility of materials and the elastic properties of materials are expanded upon during your study of composites during the Wind Energy Program curriculum. Researchers are always working on testing and refining materials such as cables so they can withstand more and more stress. Additionally, one can see an example of a guide tower clamp shown from the upper view of a communications tower. Researchers are always working on testing and refining materials such as concrete so they can withstand more and more stress. Bigger is better, as many in the building product and bridge industries would say, and it's certainly true of precast concrete products. Steel reinforcement bars add a great deal of strength to large concrete products. But rebar alone can't provide the tensile strength necessary for precast products that stretch for extended lengths. There is a bit of wizardry that imparts sufficient strength to these enormous products, and it's called pre-stressing. In more formal terms, pre-stressing means the intentional creation of permanent stresses in a structure or assembly to improve its behavior and strength under various service conditions. Pre-stressing tendons are used to provide a clamping load which produces a compressive stress to offset the tensile stress that the concrete compression member would otherwise experience due to a bending load. One can also find this idea in Gorilla Glass, where adding pre-stress to a product can actually make it stronger against deformation. Here is a great link to the Corning Glass Factory website, which can assist you in learning more about this unique material. This may be parallel to one of the object's faces. The stress is called a shear stress. The shear strain is the ratio of the horizontal displacement and the height of the object. The shear modulus is S. A material having a large shear modulus is difficult to bend. Here is an example of a machine designed to determine the shearing stress on a soil sample. Failure to determine the compressive and shearing strength of soil could lead to poor foundations and footings on your projects, and these types of engineering tests should be completed when working on bit processes. Bulk modulus characterizes the response of an object to uniform squeezing. Suppose the forces are perpendicular to and acts on all the surfaces, like when an object is immersed in a fluid. The object undergoes a change in volume without a change in shape. Volume stress is the ratio of the force to the surface area. This is also the pressure. The volume strain is equal to the ratio of the change in volume to the original volume. A material with a large bulk modulus is difficult to compress. The negative sign is included since an increase in pressure will produce a decrease in volume. B is always positive. The compressibility is the reciprocal of the bulk modulus. These solid iron shock absorbers would be difficult to compress under any degree of pressure. Solids have Young's bulk and shear moduli. Liquids have only bulk moduli. They will not undergo a shearing or tensile stress. The liquid would flow instead. This will be called dynamic fluid flow, which will be discussed later in this lesson. Stress-strain curves are in many ways the key to understanding and applying the results of simulation analyses. Stress-strain curves are unique for each material, but many kinds of materials exhibit the same patterns of behavior as loads are increased. Here we can see a stress-strain curve typical of a common ductile material, such as mild steel under tensile loading. At the left side of the graph is the region where the material's response is known as linear elastic. Under elastic deformation, the material will deform, but as the load is removed, it will return to its original shape. This can be seen if you lightly flex a long metal rod, which will bounce back when you stop applying force. The image shows 5 cylinders of different sizes and different materials. Oftentimes in a laboratory setting, a physics teacher would ask students to predict the weight of each object and order them by these weights. Can you make a guess on which one of these weighs the most? The answer is actually, well, they all weigh the same. The answer is related to density. Objects of the same volume and different densities are different in their mass. There is more material packed into a dense object than there is in a lesser density object. Notice the density gradient, which was produced by placing various liquids and solids on top of each other, allowing them to separate via a differentiation process. The more dense the material, the closer to the bottom it locates itself. Oftentimes, a density gradient can be used to measure relative density of various materials. If you wanted to know how dense a soil sample was, you could drop the soil into the gradient and you could monitor to which level the soil floated. That would be your comparative density value. Oftentimes, a hydrometer is used to determine the specific gravity of a material. It is making a comparison of the density of the material to the density of the fluid water. For a better explanation of how this works in the winemaking industry, you could go to the following URL. Pressure is the force exerted by a fluid on a submerged object at any point if perpendicular to the surface of the object. Force is placed over an area. Equation-wise, this is force divided by area, which results in what we call pressure. The units for pressure are newtons per meter or the Pascal. Do you remember the movie 20,000 Leagues Under the Sea? There is a lot of pressure on this submarine, the Nautilus, at that kind of depth. Captain Nemo would have to come to the surface slowly to make sure he didn't get the bends. Decompression sickness, or DCS, describes a condition arising from dissolved gases coming out of solution into bubbles inside the body on depressurization. DCS most commonly refers to a specific type of underwater diving hazard, but may be experienced in other depressurization events, such as caisson working, flying in unpressurized aircraft, and extravehicular activity from spacecraft. Since bubbles can form in or migrate to any part of the body, DCS can produce many symptoms, and its effects may vary from joint pain and rashes to paralysis and death. Individual susceptibility can vary from day to day, and different individuals under the same conditions may be affected differently or not at all. The classification of types of DCS by its symptoms has evolved since its original description over 100 years ago. Although DCS is not a common event, its potential severity is such that much research has gone into preventing it, and underwater divers use dive tables or dive computers to set limits on their exposure to pressure and their ascent speed. Treatment is by hyperbaric oxygen therapy in a recompression chamber. If treated early, there is a significantly higher chance of successful recovery. Pressure is force perpendicular to a surface area of the surface. In a static fluid, the pressure increases with depth due to the weight of the fluid. It is easy to show that the pressure at depth h is given by this formula, where r equals density, g equals gravitational acceleration, and P sub O equals pressure at the surface. The same question would work for pressure in a stack of newspapers. The difference is that newspapers do not push sideways. P sub 0 is normal atmospheric pressure. The pressure does not depend upon the shape of the container. In Pascal's principle, a change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. The hydraulic press is an important application of Pascal's principle. According to Pascal's principle, in a uniform fluid, pressure depends only on height. There can be no pressure gradient except for that caused by liquid pressure. This is seen in hydraulic jacks, which are used to lift heavy objects. They are also used in hydraulic brakes, forklifts, car lifts, etc. Here's a great website which explains Pascal's principle in more detail. A manometer is an instrument that uses a column of liquid to measure pressure. One end of the U-shaped tube is open to the atmosphere. The other end is connected to the pressure to be measured. The barometer measures atmospheric pressure. Evangelista Torricelli is credited with its invention. A barometer is typically a long closed tube filled with mercury and inverted in a dish of mercury. 1 atmosphere, or 1 atm, equals the following. Archimedes' principle states, a body fully or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid that body displaces. There is an interesting legend that accompanies this principle. Apparently, Archimedes was asked by a close friend or relative, King Hero II, whether a wreath, often falsely stated to be a crown, he received was pure gold or alloyed with another metal like silver as he suspected. He could not destroy the wreath to make the determination. Archimedes didn't come up with a solution until one day while he was sitting in the bath. He suddenly realized that since gold is more dense than silver, a given weight of gold will have less volume than an equal weight of silver. Consequently, the gold would displace less water than an equal sample of silver. Upon conducting the experiment, he found that a sample of gold equal to the weight of the wreath displaced significantly less water than the wreath. This insight led to Archimedes' principle.